This is an introduction to shear and moment diagrams, and let me just give you a quick feel for what shear and moment are. I think we have already covered this, but I just wanted to make sure. Shear looks something along the lines of this. Basically, you're going to have a force that is pushing the members in different directions, and it makes the material want to do this. It wants to do this. Obviously, the strength of the material and other things like that will resist it, but it will, because of the forces are wanting the material to move in such a way. Now, moments does not do the same thing. Moments look something like this. And yes, it can go the other way, but the idea is that you have bending. And this is physically what will bend, and also it's not what we're going to be talking about now, but later on there is a possibility of getting into the similar types of diagrams for torsion, and that's very possible as well. So rather than me looking at the theories and such, I just always want to dive into a problem, and that way we can kind of work our way from there. So let me draw just something really simple. We'll do a simply supported beam and rigid pin joint over here, put some wheels on this joint over here, and just, I don't know, halfway down put 100 pounds. Doesn't really matter how much. So call this distance of 5, and the whole thing distance of 10. So first of all, let's draw this said shear diagram. Okay, so let's draw it directly below. We should even line this up. So what I would suggest you doing is drawing quite literally a line that lines up perfectly with the edge of this diagram, and then extend what's going to be my x-axis outward. You can draw them however you would like. You can do them all individually, separate sheets of paper if you feel like it. I just find it easier this way. It allows me to line them up. So what I want us to do is consider, first off, that, well, we already know the reaction forces of this can be half each side. So this will be 50 on this side and 50 on this side because it's halfway. So what I want us to do is determine what the shear diagram is. And basically all that is I want you to read this like a book. I want you to look at the left-hand side and say, what force is applying at that direct moment? And if you look at that on the left-hand side, just on this, over here, on this side, you'll see that you have a support pushing upward. So I would consider that a positive 50 in force. This is just for the shear diagram, okay? Then no force. There's no force as I'm going right. There's still no force until smack, once we hit the middle. Then you realize that we now have a force that's pushing down 100 pounds. So minus 50 minus another 50. Then it continues back over to the end of the member where it comes back to 0. One thing to note, with all pin joints, your shear most likely, well, for every simply supported beam, I should say, it will always end up at 0. So that's, just use that as a checkpoint for yourself. So this shaded area indicates the shear. Well, the graph indicates the shear that is being applied, but the shaded area gives us some information of how the moment might respond. Remember, this is shear right here. This is force. Force along the y-axis. So I'm going to just say shear over here. But what if we went to the moment? I mean, how do you get moment? Moment is, what are the units of moment? It is force times the distance in units. We'll just call these feet. So if it was force times the length, then that would be your moment at that moment, at that exact spot. That's where your moment is. And what you realize is the area underneath this shear is actually your moment. And it gives you a good indication of whether it's going up or down. If you see area above the x-axis, then you can see that the moment's going up. It's getting higher and higher. However, if it goes below, then it's getting less and less. Case in point. What would this look like? You can see that 50 times the distance, which would be 5, because it's 5 to here. This distance is 5 feet. So the moment at this exact moment, right at halfway, is going to be 5 times 50, which would be 250. So if we do that real quick, you'll see a peak, which is at 250, because you can see for the rest of it, it's going down, indicated by the area below the x-axis. So really what this looks like is this is a linear line followed by another linear line right down. And here being 0, and this would be pound feet moment. Very good. So this area, this graph right here, is going to be our moment diagram. Now what does this mean? Someone was asking me, well, how can I mathematically prove this, or how can I mathematically understand this? One thing I would suggest is look at what type of function this shear diagram is. It's basically saying from 1 to from 0 to 5, it is basically 50 pounds, right? And from 5 to 10, it's negative 50 pounds. That's what the graph is saying. How can we write that? Well, we could say that to do this is like a constant, right? Well, what if we took the integral of this constant? And let me just help you out more. What if we did integral between 5 and 0 at 50 dx? Kind of makes sense, huh? Then you're going integral between 10 and 5 at negative 50 dx. Now you're starting to realize why we needed to know integrals back in calculus. This is the same thing. If we had a really complex shape for our shear, maybe rain is accumulating in one area, maybe water is flowing over it, whatever the reason is, this can help us determine how much moment is being put on the material due to these varying forces. So anyway, I hope you found this useful, and let me just kind of kick over with some examples of this very same topic.